So we're going to start the second half of our topic 6. But first, we'll do a couple warm-ups at great absolute value, and then we get into piecewise defined functions. But we'll get there in a second. So the warm-ups say graph each absolute value function and give the domain and range. So remember that when we're dealing with our absolute value function, generally speaking, it looks like this. Very, very, very similar to our quadratic. Because it kind of looks like a quadratic, it's just straighter and not curved. So in number 1, our vertex, remember, is the opposite of inside the absolute value bar, so it's -3. And then the number chilling behind the k is 2. So -3, +2 is our vertex. And then from there, we use our slope. Our slope is -2 over 1. So down 2 over 1. Down 2 over 1 the other way as well. Down 2 over 1. Down 2 over 1. And we have our absolute value function. The domain is all real numbers for our parabolas or our absolute values. Our range is not, though. Here is our vertex, so that's our maximum point of 2. So y is less than or equal to 2 because everything's below a y value of 2. Number 2, same type of thing. Our vertex is 6, -4. Remember, it's the opposite. So 6, -4. And then our slope is 1/3. So we go up 1 over 3. Can't really go too much farther that way. Up 1 over 3, up 1 over 3, up 1 over 3, up 1 and over 3. Whoop, that's 2. 3. And then just connect them the best we can. And that's our absolute value function. Again, the domain is all real numbers because our function goes all the way to the left and all the way to the right. It's not all real numbers for the range because it doesn't go all the way up and all the way down. It goes all the way up, but it doesn't go down at all. So it's always y, comparing it to our y of our vertex, which is at -4 here. Now in comparison to -4, are our y values bigger than that or smaller? Well, it's very clearly they're above it, so they're bigger. So y is greater than or equal to -4. So let's look at piecewise defined functions. How is f of x equals 2 times the absolute value of x related to a linear function? Well, so there's our function, our red function there. How is it related to a linear function? Well, really, it's 2 of them. One from the y-axis to the right, and one from the y-axis to the left. Each piece is a part of a line. So when x is greater than or equal to 0, meaning over here, the rule is y, or f of x, equals 2x, because it's just going up 2 over 1, up 2 over 1. Now, on the other side, when x is less than 0, the rule will be f of x equals -2x, because all these x values are negative. So if I plug in -2, it comes out as a +4, and that's what it has to be because it's up top here. So the slope's going down -2 to 0. We can rewrite this function as a piecewise defined function, where we say it's 2x when x is less than or x is greater than or equal to 0, and -2x when x is less than 0. Notice they're both not greater than and equal to or less than and equal to. It doesn't matter which one because they both will end up at the same spot. But now this function, f of x equals 2 times the absolute value of x, has 2 pieces over 2 intervals of the domain. So 2x and -2x we use the first one with all x values greater than 0, including 0. And for the second one, we use all x values that are less than 0 and plug them in. So it's substitution again, but right now I think we're just going to be sticking with lines. So hopefully that can help us. All right. Express f of x equals negative 5 root or absolute value x as a piecewise defined function. All right, well, let's just really just sketch a picture. What do we know about it? It's going to be very narrow, and it's going to be opening down because negative 5. So on this first half, all right, let's use f of x equals, so for x less than 0, we're talking about this side here. Well, the slope is 5. It's up 5 over 5, up 5 over 5, up 5 over 5. So it's just 5x. But now on the other side, after 0, or including 0, x is greater than or equal to 0, what's our slope here? Well, it's the same thing as what we had in the first one, but now we're going down. So it's a negative 5x. I think writing out that little sketch of the diagram will help. Maybe it won't, don't use it, but give it a shot if you think it might help. Now, 1b, same thing. So this one's going to be opening up because 2/3 is positive, but it's going to be a little bit wider because it's up 2 over 3, up 2 over 3, up 2 over 3 over here. So we have something like this. So f of x equals, for x is less than 0, and it doesn't matter which one's less than or equal to or greater than or equal to because they meet at the same place. So x less than 0, that's this side. Well, we know the y-intercept is 0, and our slope is negative 2 over 3 because we're going down. So our function for that is negative 2/3 x. Whereas on the right side, we're going up from the origin, so it'd be positive 2/3 x. And that's our piecewise defined function. We'll do one more. It's very similar to number 1a. Actually, it's probably more look at that. We know it's narrow because 3 is bigger than 1. We know it opens down because it's negative. And its absolute value, the vertex is at 0, so we know it looks like that. So again, f of x equals, and it changes at x equals 0, so we can do x less than 0, x greater than or equal to 0, like we did in the top two. So when x is less than 0, over on this side, we have a positive slope. Well, that slope is going to be the 3. So it's 3x. On the right side, it starts going down. It goes down a negative 3 for slope, and then times x. That's all we're doing there. All right, a little bit more complicated one. They give us an equation, f of x equals x plus 1 if x is less than or equal to 2, or it's negative 3 over 2x plus 6 if x is greater than 2. Well, we graph each function. So x plus 1 when x is less than or equal to 2. What I like to do, because 2 is our boundary, that's where the two lines meet, I like to put a dotted line there and know that I can't go past that. So x plus 1, we graph it like normal. Here's our y-intercept at 1. Our slope is up 1 over 1, up 1 over 1. I can't go any farther than that. So that's the right side here. On the blue side, it starts at 2, And our slope is negative 3 over 2. So down 3 over 2. Down 3 over 2. So it's really plugging in a couple of values, more substitution. Over what part of the domain is the function increasing or decreasing? The function is increasing on the left when x is less than or equal to 2 on this part, and decreasing when x is greater than 2. So this one. And it's obvious to see if you look at the graph. It's increasing, increasing, increasing. Stop here, decreasing. All right. So let's graph these. So 2a, we have a border of 2. So again, I'm going to draw a borderline at 2. And then x is less than 2. We're looking at the line negative 2x plus 3. Well, we know slope-intercept form. We know that 3 is b, our y-intercept. That is on the left side of that line, so it works. And then our slope is negative 2. So we go down 2. We go down 2. And that point is on our dotted line, so that's as far as this line goes. But we could go backwards to get some more points. And it keeps going on the left, but on the right it doesn't. Now on the right, when we plug in 2, we get, wait a minute. Sorry, this should be an open circle on 2 because it's just less than. Now we plug in the 2 to this next equation, so 1/3 2 minus 1 to get our starting point, because we don't have the y-intercept because it's not on the same side as what we're working on. So we get 1/3 times 2 is 2/3 minus 1 is negative 1/3. So it's a little bit below the axis. So it's a little bit atop of the open circle. So they don't meet here, and that's fine. Now from this point, we can use our slope. Up 1 over 3. And again, this is a little bit below the x-axis. So up 1 over 3, slightly below. Up 1, right 3. And then we connect those dots. Hopefully better straight lines than mine. All right, let's move on to 2b. Now our boundary line is going to be our y-axis at 0. So this will be for the left side, and this will be for the right side of our y-axis. Now 3x minus 5. Since it's not really included on when x equals 0, so we're going to have an open circle there. But we still have our y-intercept at negative 5. So we got a negative 5 intercept for the left equation, the 3x minus 5. Now we need to get more of the slope. Well, we can't go up 3 into the right one because it's into the other side, and that's not what we're doing here. So it's going to be go down 3, 1, 2, 3, over 1. 1, 2, 1, 2, 3, over 1. So it looks like that. Now when we start with the right side, the y-intercept is also negative 5, and because 0 is included in the set, we can color that in as a part of the second function, not the first one. We have our y-intercept plotted, so we just have to use the slope, negative x. So it's negative 1 over 1. So we rise 1 by going down 1 and to the right 1. Down 1 to the right 1, down 1 to the right 1, and so on and so forth. And that's what our piecewise function looks like there. So nothing too crazy. Let's try and do another one. So our boundary line is 1 this time. So that's where our functions switch. So for x is less than or equal to 1, so this is going to be a shaded in circle. And our y-intercept is -2, which we can't get to because the y-axis is to the left, or where x is less than 1. So the y-intercept is 0, -2. It is shaded in because it's less than or equal to. And then we use our slope. When normally we go up 1 over 1. Actually, we can get that one. And then go down 1, left 1, down 1, left 1. So we have this line. Then, at x equals 1 again, actually a little bit x is greater than 1, the y-intercept is 3. Well, we can't use that. So if we substitute 1 in there, we get this value. We substitute in 1 for x, we get 1 for y. So 1 and 1, this is an open circle because there's no greater than or equal to. It's just the greater than. And the other one doesn't overlap it, so that's as much as you can do. Then from there, we just use the slope. Slope is -2 over 1, so down 2 over 1, down 2 over 1, and so on and so forth until you get tired. Come on. Connect the dots. Excuse me. And we have our piecewise defined function. Looks pretty good. You can erase this dotted line if you want to get rid of it. I don't care if it's on the paper when I grade your tests, so doesn't really matter. All right. The gym owner wants to purchase custom wristbands for a marketing promotion. She thinks she will need about 75 bands. Her assistant insists that ordering over 100 wristbands will be less expensive than ordering 75. How can the assistant convince the gym owner? Well, really, all this is a piecewise function. So, I guess first off, if we order 75 bands, which is what we need, that goes into this middle line there. So they're $1 each, plus 10 for shipping. So that gives us $85 to purchase 75 bands. But if we went with 100, they're 50 cents each now. And we have free shipping there. So that just costs us $50. So it's much, much, much better to get 100 bands, have some left over, but you pay, well, $35 less for getting 25 more bands. Seems like a pretty good deal to me. So how can so 100 bands will be cheaper than 75 bands. Why am I writing them as bands? Bands. And again, it's piecewise. For X values 0 to 50, they're $2 each, plus $20 shipping. And we saw the other two. All right, last one here. What is the difference in cost between one order of 200 wristbands, 2 orders of 100 wristbands, and 4 orders of 50 wristbands? All right, so we're not actually done with this. I'm going to zoom out so we can kind of organize this a little bit better. But from 0 to 50, basically they're $2 for each one, 2x plus 20. From 51 to 100, they are $1 each plus $10 shipping. And then over 100, it's 50 cents each and no shipping, so that's it. So if we order 200 wristbands, so 200 wristbands is going to be, well, $100. It falls into this last category. So 0.5 or 50 cents times 200 bands is 100. And there's no shipping, nothing to add on. So it's just $100. Now, if we order 2 100s, well, we already know 100 bands is $50, and if we have it twice, that's just 50 plus 50 for $100. So it's the same price whether we go as a big order of 200 or 2 100s. Now, what about 4 orders of the 50 wristbands? So 50 plus 50 plus 50 plus 50. So if we order 50 wristbands, it would be $2 for each one times the 50 plus 20. So that's $120. And that's just for 50. Because the more that you buy, the less you have to pay. So each one of those 50 is 120. So if you did it that way, it'd be $480. That is not a good business deal. It would just be simpler to choose that. Not much of a difference between getting 100 and 100, but getting 50, 50, 50, 50, way, way, way too much time. Not good for us.